All right. Oh, wait, your quiz. The solutions for the quiz should be up. Does anybody confirm that?
I didn't see it like 20 minutes ago. It was like 20 minutes ago.
You see it?
Check it up in the last one.
It's not up? Well, I'll take care of it right after class, and I'll do this, show you the solutions. What I want to do today, I want to tell you something. We've done with classical waveguides. We did the rectangular waveguide, right? Now, let me go through what I'm up to right now. Whitmore's book has a lot of stuff about optical waveguides, really slab and fiber optics. The problem is, to do a real good, thorough job based on the first principles, Maxwell's equations, the equations themselves get rather long, and I'll explain the boundary conditions. But the real essence you want to take from it, when you've got a waveguide, a rectangular waveguide that's conducting walls, what you want to do is know the input impedance. And you also want to know what frequency you have to be below and the frequency you have to be above that you get only one mode. You follow me? This is the essence of what you need to know. The cutoff frequency of the 1.0 mode, you want to be above that, so you propagate. But you don't want to be above the frequency where the 2.0 mode kicks in. Follow me, class? And you want to know the impedance of that waveguide, because that way when you have an amplifier or a power source that's going to drive it, you want the output impedance of that power source to be matched to the waveguide impedance. Do you follow me? Now, when we get through antennas, I'll show you how to put a small probe into the center of a waveguide and drive it in 1.0 mode and how you calculate that impedance to the best of my ability. But right now, what I'm going to try to emphasize is that waveguides, the thing you primarily need to know is electrical engineers, unless you're doing design work, is the cutoff frequency for the lowest order mode, the 1.0 mode for rectangular. Then the cutoff frequency for the next higher mode. That gives the range of operation. And then the input impedance, and it's T. You all got me on that one? That's for the classical rectangular. Now there's something called a slab waveguide. And I'll explain it. The only thing a slab waveguide is basically something wide that's a slab of material that has a thickness A. Sometimes they show it at 2H, and they put a center line here. And this has got some dielectric material right here. And what I'm really trying to do is show you the waveguide goes this way, so wave propagation is in this direction. Now I'm going to show you this. I don't like PowerPoints, but for this one, it's useful to see this. Follow me on this, class? It's just like a rectangular waveguide, except now the fields don't go to 0 at the boundaries. What happens is they start dying off exponentially. It's called an evanescent field. And that has to do with writing the equations that solve Maxwell's equations inside the guide. All right, this is going to have, inside this, there's going to be some index of refraction, call it N of the, I guess, the slab. And then outside, there's going to be some A to naught, usually free space. All right? But outside here, remember, that isn't a perfect conductor, so the electric field doesn't go to 0. And what you do is you write these equations, Maxwell's equations, inside the slab waveguide, and outside, and then you match boundary conditions, which means you what are called transcendental equations. And there's not a closed form solution to these. It's graphical in nature. But of all that, I mean, they're going to show you the field modes, both even and odd, the 1.0, the 2.0, the 0.1, the 0.2, and all manner. We'll show you these. But the real thing you have to know for this guide, just like, this is a slab, a conducting guide. We have a conductor everywhere. The thing you worry about is the lowest, I mean, you want to know what the frequency is that you have to be above so you get only one mode but not two modes. Got me? And the impedance. These guides are a little different though. Hear me on this one. Optical waveguides almost always talk about an angle of acceptance of electromagnetic energy. If you're above that angle, the thing will just ricochet indefinitely inside. If you're above that, then the wave, some of the wave will come outside the waveguide, and it causes a power attenuation. And I'll get to all this. Please try to bear with me on this one. I thought that this is the most fair way, and I'll go give you homework and explain you why I'm giving you the homework and what you need to take from it. Because if you look in his book, some of the stuff he gives you, he just throws equations out there, doesn't really explain where they come from. So it's always you start with Maxwell's equations, but let me go through this. So slab waveguide. Here's what happens in a standard metal plate waveguide we've been talking about. The wave bangs back and forth, but at the boundaries, right here and here, this is a cross-section electromagnetic of a standard waveguide. The E field goes to 0. Do y'all see this? Now what he's doing there, this is going to be a TM mode. He's showing you how the E field can vary like this, but it has to go to 0 here and here. Do y'all see that, class? Yes?
Can you post this on?
Yeah, sure. I'll put it. I mean, it's literally just a web link, but I'll post them up there. Just understand, this is what we have here is we have a full wavelength and a half, right? So that's the 3.0 mode right there. All right, but don't worry about that right now. Just appreciate what I'm showing you. That the boundaries are things where the field goes to absolute 0 at the boundaries. That's the key thing to take from this. Now, for a dielectric waveguide, what you're going to have is this. Here's the actual material where the bouncing is taking place. But a wave, outside here, there will be an electric field, and it will decay in what's called an evanescent mode. What it means is it's not propagating energy there. It's electrostatic energy that's just going to maintain it. You follow me? It's like around a capacitor plate. If you have a capacitor and you charge it up, there's an electric field around there, but that electric field is not propagating. It's just dormant, you might say, right? And you can get that energy back out when you short out a capacitor. Are you with me on this? So that's what an evanescent field is without getting into the crazy mathematics. Now, what he does, and what so many people do, including Dr. Wentworth, is they say that the fields inside this guide or any guide can be expressed as the superposition of two propagating waves that are basically going in opposite directions. They're banging around like this. Y'all follow me? You can do that, and they solve Maxwell's equations exactly. When you do that, you get something like this. The y is just a unit vector there. You're going to get a wave here that's really banging this way, and then you're going to get a wave here where that reflection coefficient is from one of these surfaces, and it's going opposite, but they're almost sequenced together. You don't have to worry about the details of the math too much here. You just have to appreciate that's the way he's going to go up and solve this. All right, now, so what does it actually look like? Well, here, one other thing with this. The K's here, you see how he has a K vector? K is really beta, all right? This is beta unguided, think of it. Now R, the reason I have sub R is because beta always has a direction sense to it. Beta unguided is going to be something that's moving in the media at this angle of theta I. It's hitting here, and reflecting and hitting here. Follow me? Now when you have these kind of guides, if you have dielectric, say air here, and you have a higher dielectric constant, then you get something called the critical angle we talked about. And if the angle here is bigger than the critical, then everything is totally internally reflected. Y'all remember that? And that's what happens in a slab waveguide. All right, more on this. I thought about how to present this. I'm not going to use a lot of high-powered math. It's going to mean nothing to you. What I'm trying to do is get at the essence that you need to know. So what do they look like? And this is probably as good as any picture of a standard type of slab waveguide. It's real wide. What it amounts to is this dimension is at least 10 times this dimension. Usually the lowest order mode it's going to be a lower frequency than this, but the wavelength would be half a wavelength plus the two evanescent fields that you go about 2 skin depths either way. And I got to show you that. Or 1 skin depth either way, so it's 2 total skin depths. And this is not going to be much to you yet because we haven't even talked that much about skin depth related to these things. But you have a feel for skin depth, right? It's the distance it takes for the field to attenuate to about 33% its value, right? And remember that 37% is maximum roughly. So at least you have an idea that the thing's attenuating out there. And again, this is where all the stuff's trapped. Somebody will ask, has anybody ever heard of you've heard of fiber optics, right? You all have, you know, fiber optics give you a lot of super fast things. It's wonderful if you get single mode fiber. It's unbelievable the data and throughput you can get. Well, for these type of things, we don't have slab waveguides like this over any reasonable distance. You don't have a slab waveguide from here to, you know, Brown 238. That would be insane. You would do fiber there. Where they're used a lot is right on chip. If I'm doing a very large scale integrated circuit chip design, and I'm doing optical stuff, then I'll take the optical out here, I'll put in, because it's cheap to do this, a simple slab waveguide. The way I can do that is I can take silicon, grow an oxide, now I have SiO2, and then just etch it off, and now I have SiO2 over silicon and air. That's a good slab waveguide. And then I'll just design it for only one mode that I'm caring about at the frequency of interest. And then literally the impedance matching is just snugging that thing up to what's called an optical sensor, either a laser emitter, and I'll try to show you more on this if I can. A laser, you know, you all see lasers that are used all the time. They're helium, sometimes argon lasers, depending on the frequency you want. And that's really a lot of the slab waveguides. You can do it at much lower frequencies, like 30, 40, 50, 60 gigahertz, but I don't see a lot of that, rarely. Most of the time it's higher frequency. So that's what you're dealing with as a standard, what they look like. It's a sandwich, basically. All right, now these are the field patterns. There's odd and even field patterns, just like you get odd and even field patterns in the actual rectangular waveguide. In a standard metal waveguide, you'll notice how the fields go to absolute zero at the interface. That's EY. He's showing you EY versus Z. They go to absolute zero, right? Are you with me, class? Now here, they don't. You see how there's this evanescent decay here, evanescent decay here. That's the contrasting the difference. The modes are the same though. If you have a 2O mode here, you're going to have a full wavelength in there. You're going to have a full wavelength here. Well, actually, it's a full wavelength if you think this being 0 and this 0. It actually starts here and ends here, a couple of skin depth in. But you don't need to really concern yourself about that. Then, now, I've thought about doing this, but I think it would be a magnificent waste of time here. The way you get these is, you remember how I start with Maxwell's equations? I get a del squared operator, right? Del squared of E plus omega squared mu epsilon E equals 0, and then I say what mode I'm in, TE or TM, right? After that, you get the possible solutions. You get some E naught times cosine kx times x plus E naught, say 2 times sine kx times x, right? And then you go there and you get it and you say, well, that goes to one part of the solution. Then there's another part, then you solve the beta equations. Well, here you will have both the sine and cosine. It will be both modes at once possible. This is important. Now the H field will have both modes possible also. Understand? So the H field will have both a cosine and a sine. I'm giving you a preview of what we're going to do. But when we take the ratio of EY to HX, that's an impedance. And this is important. The impedance looking in the direction of propagation is a constant. And the impedance perpendicular to the actual waveguide's interface with the slab with the region above it, that impedance is constant. Do you follow? Now what you end up doing when you get that, some of you will appreciate it. You're going to get equations that are transcendental. You have things equal to each other. When you take the EX, or what is that? EY over HX, you're going to get you're going to get tan and cotan, or sinh and, or tan and cotan, or hyperbolic tangent and hyperbolic cotangent. All right, there's tangent. You know what I'm talking about? You know, sinchar, cosh, all those things. They're hyperbolic. Instead of having the tan, is what? Tan is, if you remember, is sine over cosine, right? Well, tanh, A-T-A-N-H, is sinh, S-I-N-H, over C-O-S-H, cosh. Are you familiar with these at all? Exponent? How many have heard of them? Well, the hyperbolics are real common when you have solutions that have imaginary arguments, but that's for another day. I can get off. So anyway, this is where these equations come from. I don't want you to get buried in equations. That's not important right now. Here's what it is. All right, then they say the boundary conditions. We do something like that. Now I just want to make mention, here he's going to get tangent and cosh. He's going to get tan and cotan inside this region. Outside there, he's going to get in this region and here, in the cladding, he's going to get cosh and tanh functions, hyperbolics. Anyway, make a long story short on this one, when you divide, this is really getting the impedance by taking the ratio of E to H. When you do that, you get this and this. And this is just not something I want to spend time on. I'm going to tell you in your own, you can look through this and you'll see it, but it's not really that much that important. Now, I'll tell you why it's tough to solve. When you do this, and if anybody is really interested in this, come see me after 2 o'clock today. I'll go through the whole derivation with you, but it takes a good hour to start from scratch to do the fair job on this, and it's a pain. You know how those other ones, they kind of fairly quick once you got the hang. This is much longer, because then the solutions just of this equation, that's for only one mode, and here only on the inside, requires this transcendental solution. And you'll notice what they have here. They have the right-hand side of that equation versus kx times the here being graphed out. Left-hand side, the intersection points are the actual points where it will operate at, frequency-wise. Do you follow me on that? Because kx is fundamentally a frequency, right? This kxd, that is actually going to be a frequency. It's something that's a little outside the scope of what we need to talk about. I'm going to mention something else about this. You're going to hear a lot about modes. This mode right here is the 1.0 mode. This is the 2.0 mode. It's got a full wavelength in that, just about. The 3.0 mode would have 3 humps, so forth. All right. They don't ever have a 3.1 mode or any kind of mixed modes. It's always going to be, the modes will be single, either 1, 2, 3, 4, nothing else. All right. When you do these things, the mode you operate in typically is the 1.0 mode and only the 1.0. And they are the same frequency for either TM or TE. Only the 1.0 mode is important. I'll underscore that some more later. All right, now, I'm hesitant to spend too much time on this. But I'm going to just say this. When all is said and done, either optical fiber or slab waveguides fundamentally operate the same way. And that is that the angle you're coming in with, that this is the core and this is the cladding, so this is the slab and this is the outside of the slab. This angle right here has to be greater than the critical angle. All right? Now the problem with that, and I'll get to, is that means there's going to be a very limited angle of acceptance where things can actually propagate. So when you are aligning these things to work with a laser, you can't have something that's a little bit out of alignment or nothing will propagate. That's one of the things you pick up on this. I'll show you more about this in a second, but I'm going to tell you one thing to write down about, I think I'm going to stop here and get to my actual, I'll show you a couple of these things. These are some waveguides that are actually, or these are some fiber structures that are actually built. It's kind of interesting because, is anybody doing, you had your VLSI lab? Don't you have a VLSI, very large scale integration lab, at some point in your careers? You have device laboratory, right? You have silicon processing, huh?
I think that VLSI lab is like an elective.
All right. Well, it's worth taking because a lot of you will probably be working at Intel or a company like Intel, something large-scale integration. And if you're working nowadays with a lot of the companies, they're doing everything in-house when it comes to their chip fabrications. That way, the trade secrets stay there. I mean, you let it out to another house to do it for you. Everybody in the world knows what you've done, and there's no real protection for any kind of infringement on the product. Here, what they're really doing is showing you with a scanning electron microscope what these things really look like in the real world. And that's an optical micro-ring filter that separates out light of a particular color. You don't have to worry about that, but it gives you an idea of the design. Here, this is a standard type of fiber. It's built in. It's a splitter. You know what splitters are with waveguides, right? With transmission lines. If you want to get 2 TVs fed with the same thing, you put a splitter on. That's what this is at the micro level. Look at this dimensions. That's 2 microns there. That thing is on the order of sub-micron technology like that. So just keep that in mind. This is what we're talking about. A lot of times we're talking about optical guides, single mode optical guides, as well as slab guides. Extraordinarily thin dimensions, things that you're not going to just create and visibly see that. They're so small. Let me just see if he has anything else. Oh yeah, this is some of the other things. Well, here's what drives some of these quantum well lasers. These are things you haven't been exposed to yet. These are devices that are going to be from VLSI technologies, even at the quantum level now. Is anybody interested in this stuff, other quantum level technologies? If you are, if you're interested in either the use of quantum entanglement for computing and quantum computing, quantum level devices. The guy next to me is named Peng. He's from Stanford. He's working with some of that. Go talk to him for a little bit. He's a young guy, very bright, and he would love to talk to you and get you interested in this. There's a whole lot of cutting edge research dealing with these technologies. I wish I could delve into this the way I do in a graduate course, but here you're talking about 2 solid lectures on just one aspect of it, just for slabs, and then it gets even a little wilder, because then driving those things with lasers and things gets really a little out of hand for an undergraduate course. Anyway, I'll put that up there. I'm going to tell you now what you need to know. And hopefully I can shut that camera off. Because I always try to do this. If I'm in your shoes, what do I want to know and why do I want to know? Say this reluctantly, but when you're talking about wave guides, I wouldn't even worry about the input impedance. It's not necessary. The real thing is that there's an angle of acceptance for optical coupling. So anyway, when you have a dielectric waveguide, I'm going to put down what you need to know. This is going to be for a slab waveguide. This one? Tell me, is that okay, guys? Better? It's a dielectric slab waveguide. I refer to these as slabs. Almost everybody does. And let me be real clear about one thing. I've never done any real engineering with this stuff. I know the theory behind it, had to do it, but I've never used this to create a device that we actually use. So this is more of something I'm aware of. It's coffin rings. I did mine. Sorry. The people that do this are optical engineers. And they're people, optical engineers, and some of the guys that build quantum level devices use these things. I have not used them, but I'm aware of them, and if I need to use them, I know how to use them. I knew the theory behind it, but for these things, most of the stuff I'm going to be doing is I'd buy parts off a shelf. I'm not going to design them. This stuff is, to design these things requires a lot of expensive equipment that I don't have. Yeah.
Is this kind of like slab wave or laser?
Extremely high frequencies. When you're doing slab waveguides and fiber optics, these are optical frequencies pretty much. They don't have to be for slab guides, but usually, if you're going to have something, if you want to run information from one part of the chip to the other, the last thing you want to do is grow an oxide and create a slab unless you have to. If you can just put in a simple coupler there, you're going to a conducting line coupler. All right, now for a slab waveguide, here's what you need to know. If this is the dimension of thickness, they're going to have some index of, this is not the impedance, it's an index of refraction. And I'm just going to call it N of the, call it S, N of the slab. Then there's some N naught here. Now these, what I'm showing you here, in this dimension is going to be A. These are, like NS, is simply equal to the square root of epsilon relative of the slab times mu relative of the slab. For all intents and purposes, it's just the square root of epsilon relative of the slab. Almost always mu relative is 1. If it's not, I've never heard of it. Because you don't have magnetic materials in optical guides that I know of. Maybe there's some exotic that does. That's the slab. This is the index of refraction. 0 is really just the square root of whatever the material is above it and below it. And it doesn't have to be air. Remember, you can have like silicon dioxide or silicon nitride, and then you could have something above it that's different. You could have thin film diamond or something. So it doesn't have to be just air. Remember that. It can be anything. But when you have this, and that's A, for a single mode, this is only for single mode, and this is what you're worried about. You want your frequency, you want A over lambda naught, and that's the wavelength of free space, to be less than 1/2 times the square root of n of the actual slab squared minus n0 squared. Wentworth has this in his book. Really, this gives you dimensionally, or your lambda naught here is going to be equal to c over f. That is, c is the velocity of free space, okay? So this is the wavelength of free space. And it says if you meet these conditions, you set them equal to each other. Then you calculate the frequency. For a single mode, you want to be less than that frequency. Are you with me? That's the key thing. And he has it in his book. You know how if you're above the 2 ohm mode, you have 2 possible modes. This is giving you the value you're going to have only 1 possible mode. And he has it in his book. I'm going to leave this. This is really what you need to know about slab waveguides. Now, he has the field equations in there. I'll get to you in a second. Field, he has E and he has H. It's unnecessary to know those because the only way you solve them is going to be making the impedance, the normal impedance at the surface of the slabs to be continuous, and the solutions to those are transcendental in nature, class. Yes, sir.
With the subscript up there for A to S equals square root of epsilon, is that an R or V?
Yeah, it's relative. It means the relative permeability, relative permittivity.
Okay.
That's all I mean by that. So this is really the only thing you need to know, in my opinion, for slab waveguides. The rest of it, I'm not going to touch you. I'm not going to touch you.
Do you need to put anything above that square root of HS squared minus?
No, it's just 1.
Okay.
1. Now, for fiber optic technology uses a cylindrical guide. It doesn't use a planar guide. It's not square. Fiber optics, I may, if I have time, I'm going to do the cylindrical waveguide solutions for you. They're not that used that often, but for radar work we do use them because we can send out a right circularized polarized wave easily with a cylindrical guide, and then we can have waveguide filters and break off the right and left-hand polarization return. So they are used, but it's a little more involved. If I have time, I'll get to them. What I want to show you is this. When we talk about fiber optics now, this is what we get with fiber optics. What you normally have is this. You're going to have a very thin piece of fiber, and it is called the fiber. And this is going to have some index of refraction. And this is N fiber. Now, N fiber is an index of refraction. It is not the impedance. Follow me in this class? So NF right here, that's the index of refraction of fiber, is really the square root of epsilon relative of the fiber. Follow me? So if you had something like an epsilon relative of, say, 9, the index of refraction would be 3. Got me? Make sure you understand that, class, because people mess that up. That's the fiber. That's the thing that you worry about. Then right outside here is going to be a layer that's called the cladding. And this is cladding right here. And this also has, the cladding has some index of refraction, and NC, and that's equal to the square root of epsilon relative of the cladding. I'm just peeling back the layers, all right? So really, it's like a coax cable. You have inner fiber, just like you have a core line on any kind of coaxial cable, right? And then surrounding the coaxial cable, the inner copper wire, you have a dielectric. Well, here you don't have a dielectric, you have a cladding. And then the whole thing is encased in something here, and this is just called a jacket. Now, has anybody worked with fiber ever before? There's single mode fiber, and there's the flexible kind, right? Single mode fiber is glass. You don't bend it like this, it'll break. You can bend it a very small amount, and if you've ever seen them lay it, It's in these long, very large containers when they put it down carefully. Single mode fiber is something that they typically use. It's silicon dioxide, but it's glass, right? Now, a lot of stuff we just optically connect like a laser with a fiber optic tube. That's a waveguide, all right, but it's technically a multi-mode fiber. It allows many possible modes usually at the frequency conductor. But it's not an issue because let me just tell you this, with lasers, with most communication systems, how do they actually do it? Well, they take a carrier frequency, say 100 megahertz, and they modulate the frequency. They have an FM thing where the frequency varies slightly, right? And that is something that is typically done. I mean, microwave energy, when it goes through a waveguide, it's going to have a carrier frequency with a small amount of shifting back and forth. Now, the thing about that is the velocity is, I mean, it's only one mode, so the velocity of the wave doesn't change. With multi-mode fiber, the velocity changes, but the way they get around it with lasers don't work that way. What lasers are just ones and zeros when they send information. They send out a burst, and if you took a snapshot in time, you'd see something about this long, and spatially, filled with photons, and it's moving at the speed of light. Now, as it moves in multimode fiber, what it does is disperse. But there's such a small amount of dispersion over the distances used multimode fiber for the wave that it's really not a problem, because if the next ones come, say if you froze space, here's the first packet of photons. The next packet is way here. If you get a little dispersion, no big deal. You don't care. Now, if you let it go, then all of a sudden the thing will disperse and basically you can't tell the ones from the zeros. But fundamentally, that's the difference with laser communications. It's a burst of photons. You have an optical sensor, and it's either on or off. It is not trying to demodulate a high frequency signal. That's the big difference, right? That's what with optical guides. So this is the clad. I mean, this is really the fiber. This is the cladding, and that's the jacket. The jacket. All this really looks like this. It's one solid thing. You see a jacket here, and all this stuff's contained within it. Understand, everyone? So I'm peeling back the layers. The jacket just keeps critters from eating through there. I don't know if you know this, but for some reason, things made oil-based products like petrol products, like a lot of the jacketing materials. If you've ever done anything in a house, an old house, you'll see rats eating the material that cover the wires. Anybody experience this? All right, I have too. They ate up my boat wiring one time. I had my boat parked out at Riggs's place. And literally, rats got in there and chewed all the wires. I was like, what's so great about wires? It's the petrochemical stuff that they like. Well, they like it there too. That jacket is to prevent those critters from eating all the way through there. So usually, they have some kind of a metal or something there that will prevent the little critters from getting in there. But even doing that, I still have to talk, when I was talking to guys at Dynetics, Adtran, and this is the Chief Technology Officer, Kevin Schneider, and his friends, I think it was Robin Jaffe too, but I'm not Robin, but another Jaffe. They told me that they will get a call that their chip or something like this that they sell has failed, and it's not. When they go out there, actually some field engineers told me this, they'll find that rats or squirrels or something got in there and chewed through one of the fiber lines or something like that. And has anybody ever seen this on a, all right, where did you see it?
We made some power lines. That's like a plant we're working on.
When I was here years ago, it hasn't happened in a while, that squirrels used to get in there and get zapped on these, and we get a blackout. And I don't know what it is about the attraction, but it's really there. And so that's what that jacket's for, is to prevent critters. And take note, guys, if you're doing any kind of in-field engineering, if you are working for a small company like Gator or something like that, Huntsville, that does engineering, field engineering with antennas and stuff, make sure when you have cabling, it's secured, that you can't, a rat can't like just chomp through it, because they will. Yeah.
I think it's because like rodents and stuff, their teeth grow faster, so they're kind of like, they're gnawing on their teeth.
Why are they chewing on that? Why not a rock? All right. Anyway. Now, with this fiber, let me get to the equations that mean something. He's going to have a lot of stuff in his book that is kind of interesting, but not that interesting. Here's what it really comes down to when you deal with this. Let's just look at this as this is going to be an exaggerated look at the core. So, I mean the fiber. This is going to be the fiber right here. Then here's the cladding, all right? And here's the signal coming in. Now, what happens is this. I'm going to do this in an exaggerated way. We're going to have something where the signal is coming in like this. And this is really just the direction of signal. These are going to be photons, so the polarization doesn't matter in this case. Then they're going to come in, and it's going to have a certain bend, right? And because this cladding, or this fiber, NF, will be the largest of any of the index of refraction, it's larger than either this or this refractive index. It has to be for this thing to work. What happens is this will bend towards the center. So this angle, theta A, that's the angle of acceptance, is going to be larger than this angle, theta B. You can appreciate that, I'm sure. If you go from a less dense to a more dense media, or if you go from air to water and you look at the actual direction light goes, it bends towards the normal. You all know this class? Now it comes here, and it's going to hit the cladding. At this point, we want complete internal reflection. So we want to make sure this angle here, call it theta C, is going to be at the critical angle or greater than the critical angle. Can everybody appreciate this? You want to make sure everything's totally internally reflected, all right? And let me do it over here to make a little side note. So how does that happen? Here's how it happens. Normally, when we look at this, we say this region has an index of refraction, I'll call it eta 1, and this has an index of refraction eta 2. Now, if I have a certain angle here, theta A, matter of fact, why don't I do this the way the book does it? It says that out here, if this has eta fiber here, this has eta cladding here, and out here it's eta naught. He calls that eta naught. It's almost always air, so it's almost always 1. But just in case it's not, just leave that there. Now, if we look at this as eta naught, and we look at this as, now that's eta fiber, right? Follow me? I'm trying to just work on this from A to B thing right here. This is A, and this would be theta B here. Actually, what I really should do is this. I should go eta cladding, eta fibers. It'll be easier to do this, so sorry about that. Call this eta fiber, and I mean not eta, but N fiber, N cladding. And call this, I'll just call it angle 1 and angle 2. Well, the law that governs this behavior, this is lossless, is this. It's simply Snell's law. It's eta 1 times the sine here of, or eta fiber, pardon me, sine of theta 1 equals N2 sine of theta 2. And this is going to be cladding. What I'm trying to do is talk about this interface right here. Got me on this, everyone? Now, the reason I'm doing this is I want this angle to go to 90 degrees. And that means everything's internally reflected. You all see that, class? So if sine theta 2 goes to 90 degrees, the sine of that goes to 1, doesn't it, class? Are you with me? So if it goes to 1, I get this. And then I get sine of theta 1 equals NC over NF. And really my theta 1 that I'm showing you there corresponds to the theta C right here. Are you with me, everyone? So this is theta C. Now box that. I did that for a reason though. So I've got this angle. Now this angle has to be equal to that or greater in order for total internal reflection. If it's less than that, then some of the actual electromagnetic energy is going to come out here and just radiate into free space. With me? Or into whatever NC is up there, the cladding. It's never going to be useful to us. It's going to basically disperse. Now if I have that angle here, I want you to take a look at it. This angle, the cosine of this angle is the sine of this angle, isn't it? Y'all agree with me there? So now I'm going to say this. If I look at this, Now I'm going to look at this boundary between here and here, and I can say that eta naught, that's here, times the sine of theta A is equal to eta fiber, or n fiber, times the sine of the actual theta B. Just watch this now. You all agree with that?
These are all ends, right? Not etas.
They're n, pardon. It's n. It's the index of refraction for all these. If I said eta, I'm sorry. It's all n's, index of refraction here. Now if I have this, what I want to do is get a relationship between sine of theta A and just the actual materials. Do you follow me on this? No angle. So here's what I do. I come down here and I take a look at this sine of theta C. And what I can say is that this can be equal to NF times, if you look at this, the square root of 1 minus cosine squared of theta B. This is one way to do it. Now, think about sines. If you take sine and square it, right, you get sine squared. Take sine squared is equal to 1 minus cosine squared, isn't it? And if I take the square root of that, I have sine all over again. Do you all follow me, class? I have that equal to eta naught sine of theta A. Well, now I take a look and I see that when I look at this, what is the sine of, right here, the sine of theta C? Well, sine of theta C is the opposite over hypotenuse, right? Isn't that right, class? That's the sine of theta C. Isn't that also equal to the cosine of theta B? You agree with that?
Yes.
So it's cosine of theta B, and therefore what I can do is say that this cosine of theta is equal to this, and therefore wait a second, I want to do this. I want this, so I'm going to take this divided by n naught. Give me 1 second here. Now, here's what I'm going to do. I'll do this. I got this wrong here. The sine of theta B here would be equal to the cosine of theta C. And if I look here, this sine can be written as the square root of 1 minus cosine squared of theta C is equal to NC over NF. Sorry about that. And that means if I go ahead and square that, I have 1 minus NC over NF squared. Square root of that is equal to cosine of theta C. Here's what I'm up to. That sine, I go ahead and square it, I get sine squared, and I take the square root. Square root of sine squared. Well, sine squared is 1 minus cosine squared. This is what I'm up to. Once I have 1 minus cosine squared, I break out the cosine by itself. So I go ahead and square that, take 1 to the other side and change signs, and I have cosine of theta C is that. Then I come over here and I substitute in for that, and now I have NF over N naught. And the cosine of theta C is the square root of 1 minus, and then it's going to be NC over NF squared. And that's going to be equal to the sine of theta A. And therefore the sine, you can write this one down, is equal to, and it's just going to be equal to the square root of NF squared minus NC squared. Now those are the index of refractions. If you like, you can put down just epsilon relative of the fiber minus epsilon relative of the cladding. Epsilon relative of the fiber minus epsilon relative of the cladding. And here's the thing, this is very small. In the book, he has an example for typical values of NF and NC, or epsilon relative fiber and epsilon relative cladding. And the sine of that angle is the sine of 4 degrees, 4.4 degrees. Here's what it means to you and me, and why it's so important. It says for this thing to work right, the alignment of that fiber, the optical fiber, with the laser light can't be more than plus or minus 4.4 degrees from the normal. Now, if you get less than that, suppose you get down to, say, 0.5 degrees. Well, you don't realize what 0.5 degree is when you're creating a lot of things unless you do it regularly. That is a very tough alignment to get. So a measure of the, you might say, of the usefulness or the goodness of the optical waveguide, single mode optical waveguide, is what's called the numerical aperture, or the sine of theta A. This is called NA. He talks about in the book, and NA is simply the numerical aperture. And I want to tell you, the larger that value, the better. All right, but the way you get a larger and larger value is usually difficult to obtain, because usually what that means is that the cladding, you would like this to have a much smaller index of refraction than the fiber, and that's hard to get and work with. It just is. You know what silicon dioxide, the index of refraction, or the relative permittivity of that? Anybody? You can look it up. It's somewhere less than 12, right? Isn't it 10? Anybody? 10 something? Silicon's about 4.4, I think, undoped. What'd you get for sand? Look up sand or glass. Anybody? You got your Google search going, right?
We're looking up the permittivity of sand.
No, look up the index of refraction or relative permittivity of glass. Or silicon dioxide, SiO2.
Silicon dioxide is 4, silicon is 11.68.
Silicon dioxide is what?
4.
Oh, I had it backwards. 4. So the square root of that is 2, right? When you talk about materials next to that, you're going to see the difference is going to be fractions of what you can put around it. So that means that acceptance angle almost always is extremely small. You're right, silicon is the one was higher. My bad. So that, in a nutshell, is what I want to talk about today. There are equations in his book for how many modes you're going to get at a given frequency. This would be for multi-mode. They use multi-mode fiber for short range. The fiber that's of interest to most of us in engineering are going to be single-mode fibers when they're stringing them a long distance, because, and that's optical engineering, that's a little bit different. Now, I've got 2 minutes. I'm going to tell you where I'm going next. A lot of this stuff in this chapter is just, it's giving you information items, but it's not based on a first principles approach, except for the rectangular waveguide. That one is. And it's from first principles, and it shows you how to solve it. What we're going to do next is antennas. The perspective on antennas is, for me, is this. You don't need to write this down, but I want to draw this, and hopefully you'll appreciate it. Antennas have one specific thing that they do, in my opinion. They focus electromagnetic energy. That's the only thing they really do. They don't in any way amplify. They don't do anything in terms of signal shape. The only thing they do is focus electromagnetic energy. Here's the way we deal with antennas, and I'm going to tell you this is the easiest possible way you can get it as an understanding. When you think about antenna, first you say, if you had some system, this is always the symbol for an antenna, and you're putting in power, transmitted power. If that antenna didn't do anything to shape the signal, then if I come out a distance r away, the power density here, average power density, would be equal to the transmitted power divided by 4 pi r squared. That should make sense. If you're putting out 50 watts and I go out a distance of 100 meters and it's uniformly distributed, it would be 50 watts divided by 4 pi, and then it would be 100 squared. That would be the power density. And the power density would fall off as 1 over r squared. Does everybody understand that? So what does an antenna do? Well, an antenna takes this equation and it has something called gain that we'll get to. We'll derive gain. The only thing gain does, it takes this and multiplies it by gain. But gain is a function of the angle theta and phi. Usually when we talk about gain, we talk about something called the bore site of the antenna, at least in radar. And we talk about angles off the bore site. There'll be a theta and a phi angle off the bore site. And that's where the gain will change. It'll be a maximum. It's what's called a bore site, where the antenna is pointing all its energy, its peak energy. When you go off there, you're going to get less than that, and then you get something called side lobes. With the antenna, the key thing is what an antenna does, it focuses the energy. The measure that focuses the gain. I'm going to give you some reading on that. I'll give you some homework related to this stuff. Now, you might tell that I'm not particularly happy with the treatment of this, because the way I like to do it is from a first principles approach, and it would be a little bit beyond the scope of this class. So he's trying to introduce you to it so when you get out in the real world, or if you go to grad school, at least you're familiar with the terminology and the effects. Did you have a question? Yes. Did somebody have a question? Okay, good. You're the